All right, guys, so I'm going to share my screen here. We're going to be taking notes. It should be Thursday. And we're moving into derivatives. So hopefully you watched the video notes from yesterday that just talked about average rates of change again, which we've talked about, which is an AROC. And then an instantaneous rate of change, which for us is, just a second, I'm trying to share my screen, which we sometimes call an IROC. So once I share here, hopefully it'll go. All right, here we go. So I'm going to hop on to the notes first, but you'll need a calculator in this section as well. So I would take out a graphing calculator. Don't use Desmos. Use what you'll use on the AP exam. And then also, I would suggest that if you don't have one, I think there's one in your, what's that called? I don't know. I can't even remember the name of it. All right, let's start. So we're going to do something called the tangent line problem, which is actually really important. The problem with it, it's usually about the third time that I run through this that kids go, oh, now I get what it means. But I'm going to go extra slow. And I'm going to talk about a secant line first. Secant line connects 2 points. Like you've heard it with circles in geometry, that this is a secant. A tangent line from geometry just nicks the circle, and that's what a tangent line does in calculus, is it just nicks the curve or nicks f of x at a single point. So the secant line is there in purple, and the tangent line is here in red. And we're going to be working with both of these. The secant line slope is not calculus. That's just the slope of a line through 2 points, change in y over change in x. But the slope of the tangent line is calculus because I only have 1 point and I need 2 for slopes without calculus. So that's where the calculus comes in. So down here, just when it says to draw 3 tangent lines, one that has a slope of 0, a slope of 0 would have to be horizontal. The only place or places that I can nick this curve horizontally is right here and right here. It's going to be really important later when we get to something called optimization, when we're trying to maximize and minimize things that are changing over time, because the maxes and mins occur where that slope of the tangent line is equal to 0. So that's actually very applicable. We also need to have a slope of about 2. Well, that has to be pretty steeply uphill, and I'm only going uphill on this side of the curve. So let's say that has a slope of 2, and then I could draw one over here as well. But those are ones that have a slope of 2. Slope of -0.5 would have to be on a downhill part of the curve and not very downhill, because that's pretty gradual. So maybe this purple one has a slope of -0.5. Just so you get used to what are tangent lines and what does it mean to talk about their slopes. So now when I go up here and I go back and I draw this secant line, I'm going to label the points. I'm going to call this one is at x. My curve is y equals f of x. So if I wrote this, I'd say it's x comma f of x. Then what I'm going to do is scoot over. And the amount we scoot in our book, which we're not using right now, but we actually are, we're just not in the book. They use h. Some college textbooks use delta x for a change in x, but we're going to have a little change in x that is going to move us over to this new point, which would logically become x plus the change in x, or x plus h. So if this had been at 3 and my change in x is 5, then I'd be over at 8. That makes sense, right? So when I write this point up here, it would be the point x plus h would be the x coordinate, and f of x plus h. All right, so what I want you to look at is the slope of this line. Okay, let's write it out. Let's use our algebra 2 that says you do change in y over change in x, which is y2 minus y1 over x2 minus x1. This is change in y over change in x slope from algebra 1 through geometry. Now, the bottom of this is the slope of the secant line. I'm going to write m sub secant equals. The bottom of this, the x's cancel. So in this first one, it says, what does this expression represent? It represents the slope of the secant line. Just using a little algebra 2. What does it simplify to? Well, once those x's cancel off, it simplifies to something that should be familiar to you, because I had 2 of these on your last test where I had you find the limit, but watch where that's going to come in. So this right here is what it simplifies to. Sometimes some people will call that a difference quotient. All right, so back up here, now I'm going to draw a tangent line to the curve that hits the point right here. Now you can see that this blue tangent line is pretty different in slope than the red secant line. So if I were to use the red secant line to approximate the slope of the blue one, it'd be terrible. And then it becomes, well, what could make it better? Well, how about if I make x a little closer, which means I'd be making this h a little smaller. I'd move over less. Then I'm going to make it even a little closer. Well, now it's getting a little better. So notice h is shrinking and shrinking. I'm pulling that h back in here and saying, you know what, don't go so far away. Stay very close. Well, how close would I have to get to x? For the tangent, I'm going to draw a better tangent line here, by the way. For the tangent line slope to be exactly the same as the slope of the secant line, well, I would need h to get so close to x that if he breathed, x would feel it. Okay, I can't land on x, because if I did, then what would happen is I'd have f of x minus f of x. I'd have 0 over 0. But I can certainly do this. I can certainly take the limit as I have h approach 0, which basically means he's creeping up. The secant line is creeping up on that blue tangent line and getting so close to having the same slope. And so when I do the limit and have h approaches 0 of the slope of the secant line, this is what we call the slope of the tangent line. Okay, so it says as h, the distance between the x values and x plus h approaches 0, what happens to the secant line? It approaches, or darn near lands on top of, the tangent line, so that their slopes become identical. What do we call that? Well, this becomes the slope of the tangent line. But it gets the name, the derivative. So when I say what's a derivative, you're going to tell me slope of a tangent line. If we're talking about in real life, what that is if this was charting time and this was position at a given time, right here is my average change in position over change in time, or an average velocity. Right here at this particular time, the slope will give me what's called an instantaneous rate of change, or what's happening at that instant. So we have lots of words for this slope of the tangent line. It's called the derivative. It's called the instantaneous rate of change, or the IROC. So this is what you need to think. When you hear the word derivative, you're thinking slope of the tangent line. When you hear what's the slope of the tangent line, you say, I find a derivative. That's what they mean. Okay, so the slope of a tangent line is a derivative. So let's write it out. We're going to use the notation that the derivative of f, the slope of the tangent lines on the curve of f, maybe it was a parabola that opened down, maybe it was negative x squared. The slope of the tangent line anywhere on the curve is going to be called f prime. This little thing means prime, and that's what we say, and f prime of x means the derivative there. So if this was over at x equals 3, f prime of 3 would mean, hey, what's the slope of the tangent line there? So when you're finding slopes, We're going to call them derivatives. We're going to get them by taking a limit, and this is the only day we'll get them this way. Today we have to do, it's actually, to be honest, this section is one of the harder ones in chapter 2 because the whole rest of the chapter is, well, could we make this process less labor intensive? So it's f of x plus h minus f of x over h as h creeps up on 0. Remember, this is the slope of the secant line, but as that change in x approaches 0, that lands on top of the tangent line. So just a little notational fluency here. When you see f prime of x, you read it f prime of x, and it means that it's the derivative of the function at x. And remember, y equals f of x are sort of interchangeable. When I say f of x, you think y. When I say y, you think f of x. So likewise, y prime is also the derivative. This is actually more shorthand, but it's nice because it'll get used in some stuff that gets messy, so it doesn't look so messy. The next thing, and this is the best one, it's the most formal one, but that really is what you're doing. That d y dx means change in y over change in x. You're used to hopefully seeing this in pre-calculus or algebra 2, delta y over delta x, where this symbol you were hopefully taught meant change in for slope. Well, as that change approaches 0, we call it dx. So when they're really tiny changes. I always get kids who say, what's the difference between delta x and dx? And I say, this is any change in x. It could be 7. This is a change that approaches 0. It's a very tiny rate or very tiny change. This means take the derivative of f with respect to x, and we'll be talking about what that means, but all of this is notation for taking a derivative. And I'm going to use it all interchangeably so you get used to that notational fluency. But if I say find f prime of x, you're going to be like, I need a derivative. I need a slope of a tangent line. If I say find dy dx and y equals x cubed, then my dy dx will be some function of x. So that's what this tells you. That will tell me the slope anywhere on this cubic. So it's a slope. Slope, 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 slope of a tangent line to y or to f of x. So let's get a visual of what's happening here. So first thing I'm going to do is go do the very first run through of evaluating a derivative, a slope of a tangent line, which I've said is the limit of the slope of the secant line. So it's f of x plus h, sorry, I needed a drink of water, minus f of x over h. Let's go evaluate that. And that's why there were 2 of these on your last test. Most of you did really well on them, so it should be a smooth transition into this section. But so when we do f of x plus h, there's a reason for why I have you do stuff. I didn't just have you do this in your limits chapter just because I knew it was coming up. So what we do is we put x plus h in for all the x's. We FOIL this guy. When you FOIL them, you'd have firsts plus outsides and insides, which is xh plus xh plus lasts. Okay, I'll distribute this in, and I'll have a minus 4x and a minus 4h, then a plus 1. Okay, that's f of x plus h. That is this part is all of this stuff right here. Well, it also says that I need to, that was just sort of grunt work for f of x plus h. I'm supposed to take the limit as h creeps up on 0, the change in x creeps up on 0. So I have a parabola that opens down. I'm working with the slope of a secant line, but I'm going to keep having that change in x collapse in, be 0, so I have the slope of the tangent line, and that is called the derivative. So the next thing I need to do is take that stuff I just circled in yellow, the f of x plus h, I'm going to rewrite it. I have a negative x squared minus 2xh minus h squared minus 4x minus 4h plus 1. There's my f of x. plus h. But then I'm supposed to subtract off f of x. So when I subtract this off, all those signs are going to change. So I'm not going to write it down and distribute it in. I would have a positive x squared, a positive 4x, and a minus 1. Now I'm taking that limit. So I just rewrote that whole thing. All right, now if you remember from our limit chapter, what happens is anything without an h in it better cancel. Well, I have a minus x squared, there's the plus x squared, has an h in it, has an h in it, minus 4x plus 4x has an h in it, plus 1 minus 1. If you do that process correctly, evaluate this difference quotient correctly, everything except the terms with h in will cancel. And what that'll allow you to do is factor that h out, and I'll get a negative 2x minus h minus 4 all over h. Now this is where some of you on the last test, you got all the way down to here, you canceled, but then you put 0 in for the x term. This is h approaching 0. It goes right here. And what I'm left with is a function of x, negative 2x minus 4. This function is called the derivative. We can call it f prime of x. We can say dy dx. We can call it y prime. We'll call it all in this class. But this is the derivative of this function. What does it do for us? Well, let's go down here. I now have this function graphed right here. Right, so this is the graph of y equals f of x, an upside down parabola that's pre-graphed. Let's go see what this function that we just created by doing that limit process gives me when x is negative 4. I would say the derivative of f at negative 4 is equal to negative 2 times negative 4 minus 4, which equals 4. Remember I told you derivatives are slopes. They're slopes of the tangent line there. By there I mean at x equals negative 4. So let's go to x equals negative 4. And right here, let's draw a really neat tangent line. And you'll notice just by observation, it looks like it's going up 4 over 1. It looks like it has a slope of 4, and it actually does. So this function right here will give me a slope anywhere on the curve of the tangent line. So let's go see what happens at negative 2. The most important thing for derivatives happens at negative 2 because f prime, let's call it on this, let's change our notation. If I were to go to the dy dx notation, that means find the derivative of y with x as the independent variable when x equals negative 2. It's the same notation, and it would also be called f prime of negative 2. Okay, just so you get used to the notation. It'll equal a negative, and then I put in a negative 2 squared. So I'm going right here. I've got negative 2 squared, which is a negative positive 4. And then I have, sorry, I completely lied. I'm putting it in the wrong one. I need to put it in the derivative. So I'd have a 4 when I put negative 2 times negative 2 minus 4, and I get 0. Remember what I said? I said these derivatives are slopes of tangent lines there. And by there, I mean at x equals negative 2. So now when I go on the graph, and I'm at negative 2, and there's a lot of notes today because it's the beginning of a new topic. You'll notice that the slope there at the vertex of the parabola is 0. So it makes sense. I'm not going to do the next one. So it says use a ruler. Don't need to. It says, what does it appear that this derivative gave us on the actual graph of f of x? It gave us a function, basically a function of x. If I know the x value, I've got a function that outputs the slope of the tangent line for any x value on the original function. Suppose I wanted to know what f prime of 10 is. What that'd be is the slope of the graph when x is 10. Well, you can see it's going very, very, very steeply downhill. Can't quite see it on my graph, but I can tell you definitively that the slope there would be negative 20 minus 4, or negative 24. So does your calculator do this? Indeed it does. So that's where I'm going to now go to a different screen. And I'm going to bring up a TI-84, but I also have the keystrokes for the Inspire. So I'm going to go back to my share screen here, and I'm going to hop on my graphing calculator and show you how your calculator does this. Let me clear off the statistics I was working on. So we hit the Math 8 button. So you have this Math button. I'm going to be saying Math 8 and Math 9 a lot in this class. Math 8 is a derivative button. We want it to be a function of x, so we put a little x right there. It'll go in the parentheses, and that's where you put the original function. Now, instead of doing this one, I actually think I want to go back so you can see it do the derivative of this guy right here. So see me circling it in yellow? Let's go take the derivative on that parabola, the negative x squared. Whoopsie. Negative x squared, what was it? Minus 4x. And then we had a plus 1. And then it says, where do you want me to take that derivative? Well, we did it at negative 4, and we did it at negative 2. Let's just validate it at negative 4, shall we? So let's just go negative 4 and hit enter. Notice it spits out a 4, and that's what we got by hand. My calculator knows how to take numerical derivatives. I could do that exact same thing at negative 2, and I would tell you to try it, and you would get a 0. Inspire, these are your directions, so you might want to pause. All right, so this limit as h approaches 0 of f of x plus h minus f of x gives you the slope of the tangent line, or a function that gives you the derivative. And then you can plug a number into that function to get the slope. But there's something called the alternative form. We don't use it much. You might see it once on the AP exam, if that. So I'm going to cover it more briefly than the other one. So suppose I didn't want to know the derivative anywhere along this curve, like for any x value, but I wanted to know exactly what happened, and you can just watch this, at any specific spot, like maybe at 2. Right? So whatever this curve is, this would be the point 2, f of 2. We're still going to head out and make a secant line, but we're going to call the other point just a plain old x, f of x. So notice I have a specific point that I'm working with on this one. Well, the slopes, sorry, I'm trying to erase because that should say f of 2, and it says f of x. All right, well, the slope of that red line is change in y, and you don't need to write this down, just watch. Change in y over change in x. Boom, 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 boom. But if I want to get the slope of the tangent line there, I'd have to move my x closer and closer and closer and closer and closer and closer to 2 for that secant line to match up with the tangent line. So this is a limit as x approaches 2. It's called an alternative form. Your answer is a number. And I'll do it one with both of them so you can see what I mean. So we're going to go work with the alternative form of the derivative to find the derivative on this curve at x equals 1. All right, well, what does that curve look like? It's the square root function that would shout out from negative 1/3 like this. What will my answer give me? My answer will take me to 1, plug it into f, and do the square root of 4. So it'll take me to this point 1, 2, and the answer I get will give me the slope of this purple line. I just want you to see the visual of what you're going to find at that specific point. So my answer is going to be a number. So here's what I do, is I'm going to follow this model, my derivative, slope, at specifically 2, not at any x value like we did up there or on the previous page, is equal to the limit as x approaches 2 of f of x, square root of 3x plus 1, minus f of 2. Well, what's f of 1. Sorry, it said a equals 1. So minus f of 1, which is 2, right? So minus 2 all over x minus 2. Okay, so that's how you use the model. In this scenario, this is the f of x, the a is 1, f of a is what you get when you plug in here, so you just plug it all in. Now this is why we learned how to clean up stuff last chapter, because it's coming at you with these derivatives. So f prime of 2 is going to equal, we multiply the top and the bottom by the conjugate of the one that has the root in it. So that's why if chapter 1 didn't go well, I was really worried, and I contacted some of you, and I'm like, you might want to revisit that because it's not going away. We just build off of it. So I'm going to multiply the top and the bottom by the root, the conjugate of the root term. A couple of you on the last test changed this as well. You only changed the link between the two parts, okay? Not under the root there. So then when you FOIL, you'll be having the limit. Don't drop your limits. It's bad notation. Firsts will pop off the root, and I'll get 3x plus 1, and then I'd have minus 4. So I'd have 3x plus 1 minus 4, or 3x minus 3 on the top. Outsides and insides cancel. Something's goofy here. Oh, I see what it is. I did it again. It's x minus a, and a is a 1. Sorry, I keep thinking of this 2 for some reason, stuck in my head. But by the way, that's actually kind of a learning thing here, because I knew something was goofy, because I knew that that x had to cancel. Okay, so I knew that because 1's causing a 0, I know that needs to cancel, and I do have an x minus 1 hiding out in the numerator. So I have 3x plus 1, it's root, and then I would have the plus 2. All right, moving right along here. So let's go take a look at what happens on the top. I'll factor. And again, I don't give this long of notes very often, but when I do, it means they're important. So, and again, it's a limit. I keep putting that 2 in there. I'm sorry. It's at x equals a. A in this scenario is a 1. I'm not going to remake this video, though, so I'll redeem myself on the next one. So now when I plug this in, I'll get the 1 on the top because it canceled right here, right? And then there was a 3, so I have the 3 left on the top, and on the bottom I'll have the square root of 4, which is 2, plus 2, which is 4. What that means is the slope here is 3/4. We call the slope there the derivative at x equals 1, okay? So notice this alternative form gives us a number. So now I'm actually going to do it both ways so you can see both of them running in. So I have a hyperbola 2 over x. Let's see what that guy looks like. And this will be the last one that I do, because I think that, yeah, so this is the last one for this set of video notes. The other ones will be for homework. So this is considered classwork. The other video notes are for homework, and then the worksheets actually for the next 2 sections won't be turned in. You don't need to turn them in until Monday morning. I'll give you a little time over the weekend to get your poop in a group. So here's the hyperbola. Here's the hyperbola. We're going to hop on it. You might say, how do you know that? Because y equals 1 over x should be a parent function that you had in pre-calc that you remember. So what we're going to do is hop on at x equals 3. 1, 2, 3. I'm going to be at the point 3 comma 2/3 a comma f of a in this scenario, because I'm doing this x approaches a analogy. I'll be getting the slope of this tangent line pretty gradually downhill. I'm going to do it 2 ways, using the alternative definition of the derivative, which will spit out a number. Let's go do it. I'll be taking the limit. In this scenario, a is equal to 3. F of a is equal to 2/3. So I take the limit as x creeps up on 3 of f of x, 2 over x, minus f of a, the y value there, 2/3, all over x minus what you're creeping up on, 3. Now notice if you put a 3 in right now, you get 0 over 0, which is what happened in our limits chapter. And we said, that needs more work. That's where we clean up the complex fraction. We say 6 minus 2x all over multiply across 3x collapses as a product. So you should be pretty good at that from last chapter unless you didn't practice it, right? Our goal is to get that issue to cancel. The issue, the thing that's causing the 0 is the x minus 3. It means it or its opposite must be living on the top. We'll take a look when I factor out a 2. I get a 3 minus x there. Now these two cancel. Be careful though, because on your test I put one of these and a lot of you said it cancels to equal 1. And I just took 1 point off, but it cancels to equal -1 when you have those opposites. So be careful that you watch out for that. So this would be a -2 over 3x. Now when I plug the 3 back in, it means the slope of that line is -2/9. What do we call that? We call that the derivative of f at 3. Or y prime at x equals 3, or dy dx when x is equal to 3. It's a number that gives you the slope of the tangent line. Now I would challenge you to go to your calculator and go hit Math 8. It'll say dd and enter an x. It'll ask you for the function, hit 2 over x. It'll ask you at x equals what and put 3, hit equals, and it'll give you the decimal version of this, -0.2 repeater. Okay, so your calculator's been programmed to take these derivatives. You're going to see where they're used in the real world later in the course. Right now, we just need to know how to take them, and we need to understand what we're finding, the slope of a tangent line. All right, so now we'll go do it using what I call, this is the more important because this doesn't just spit out a 2/9. This formal definition of the derivative, also known as the limit process, will give you a function for the derivative, a function of x, so that all you have to do is plug the x value in and it will give you the slope anywhere. Over here, maybe at -4, or here at -2. It's not just at one spot, it's everywhere along the curve as long as it's in the domain of the function. So this one won't work at x equals 0 because there's an asymptote there. So let's go write our function down again. My f of x was equal to 2 over x. Okay, and my f of x plus h would then be 2 over x plus h. So when I do this difference quotient, also known as the definition of the derivative, which will spit out a function for the derivative, I do the limit. As h creeps up on 0, of f of x plus h minus f of x, I don't know if you can see that, that's an f of x, minus f of x all over h. Now, if I put in a 0 for h, I'd get 2 over x minus 2 over x over 0. I'd get 0 over 0. That's a problem. So again, I'm going to clean up that complex fraction. I'll put my limit on in just a second. I do 2 times x minus 2 times x plus h, which would be a minus 2x minus 2h. That's my criss minus cross all over multiply across. So you got to multiply those two. Boom, criss, cross, multiply across, and it collapses as a product. Just like what happened last chapter when we were doing our limits, anything without an h will go. I'll then be able to factor the h out, gone. And now when I plug in the 0 for h, I'll get -2 over x plus 0 times x, or x squared. That's a function that gives me the derivative anywhere. Well, my goal was to find it at x equals 3. So f prime of 3 will be -2 over 3 squared. Notice it matches. So you might say, well, why do we have 2 methods? There just are. Which one's better? This one. Because there's an infinite amount of answers I can get. I don't have to go through this whole process to figure out, well, what's f prime of 10? F prime of 10 is -2 over 100, or -1/50. All right, so that's it for these notes. So let's talk about on the bottom what you should take out of here as far as the language. All of these things are the same. The slope of the tangent line to f at a, we call f prime of a. The instantaneous rate of change of f at x equals a, f prime of a. The derivative of f at x equals a, f prime of a, and the limit of the difference quotient is f prime at a. All right, so a lot of different language that goes with it. We are done. So this is it for today's notes, done today. With the notes part, your homework isn't a worksheet yet. It's the second part of the notes. So what you'll be uploading on the Google form is both pieces of notes. So you actually will have another video to watch as homework. I would suggest, oh, maybe keep watching now, or do it at home tonight. So one more video to go. And so starts our journey into derivatives.